When Commander Reed Wiseman said he needed to hug the engineer responsible for Artemis II's heat shield, he turned a technical component into the symbolic center of the most remote crewed spaceflight in history. Why did one piece of hardware become emotionally more important than the entire mission? The shield's job was to slow Orion from nearly 25,000 miles per hour to 300 miles per hour, using atmospheric friction alone. And there was no backup if it failed. This was the first time since 1972 that humans personally bet their lives on thermal protection designed for lunar speeds, making re-entry survival the real hinge of the entire Artemis program. By the end, you will understand exactly why the shield became the mission's defining technical risk, what made its performance so charged, and what changed when it worked. The old story is that heat shields are mature technology, proven by decades of spaceflight. The contradiction is that Artemis II's shield faced conditions no crewed system had survived in over 50 years, and the uncrewed test flight before it left unexpected damage that made the second attempt anything but routine. Here is one concrete reality check before we go deeper. During re-entry, the shield endured 5,000 degrees Fahrenheit, roughly half the temperature of the sun's surface, while the cabin inside remained a steady 75 degrees. The mission succeeded because millimeters of ablative material carried extreme heat away from the capsule as it vaporized, and post-flight analysis measured the exact millimeters lost to refine models for the moon landing that comes next. That measurement gap between prediction and reality is where the emotional weight actually lives. Re-entry is the only phase of spaceflight with no possible abort or do-over. If a docking fails, you try again. If an engine underperforms, you adjust the burn. If the heat shield underperforms, nothing else can save the crew. This is a one-time event that either works or ends the mission catastrophically, and the crew knows it. The shield is a single point of failure, meaning there is no redundant system waiting to take over if the primary layer cracks, chars unevenly, or sheds material faster than predicted. The old model assumes that if ground testing and computational modeling agree, the shield will perform as designed. The contradiction is that Artemis I, the uncrewed test flight, returned with unexpected charring patterns that engineers did not fully predict, creating a gap between what the model said would happen and what actually happened. That gap put immense pressure on Artemis II's redesigned shield to work perfectly, because the next crew would be inside. The memory of the Space Shuttle Columbia, lost to a thermal protection failure in 2003, made this the mission's highest stakes technical risk. Columbia burned up during re-entry because a piece of foam damaged its heat-resistant tiles during launch, and the damage went undetected until it was too late. The lesson was not that heat shields are unreliable, but that re-entry protection must be treated as the most unforgiving system on the spacecraft. For Artemis II, that lesson turned the shield into the program's emotional center, because if it failed, the entire architecture of returning humans to deep space would collapse in the most visible way possible. Orion's heat shield is the largest ablative heat shield ever built for a crewed spacecraft, measuring 16.5 feet across. The material is designed to intentionally char and burn away, carrying extreme heat away from the capsule as it vaporizes. This is not a flaw. Ablation is the mechanism. The shield sacrifices itself in a controlled way, so the capsule behind it stays cool. Technicians filled over 180,000 individual honeycomb cells by hand with a special heat-dissipating material, a process that takes over a year and requires specialized ovens and high-precision machining. The old model assumes this hand-packed structure will ablate evenly and predictably. The contradiction from Artemis I was that some cells charred more than expected, and others less, creating a pattern engineers had to explain before clearing the next crew to fly. The shield had to survive not just heat, but a sequence of punishing conditions that no single ground test could replicate. Before hitting 5,000 degrees, it spent 10 days in the sub-zero vacuum of deep space, a cold soak that changes material properties.
Then it hit the atmosphere.
At Mach 32, 32 times the speed of sound. Far more punishing than a return from the International Space Station. Returning from low Earth orbit means re-entry at roughly 17,000 miles per hour. Returning from the Moon means 25,000 miles per hour. And that difference is not linear. Kinetic energy scales with the square of velocity. So a 50% speed increase creates more than double the heating. The crew returned from 6,400 miles beyond the Moon, hitting the atmosphere with more kinetic energy than any humans in history. The old model for re-entry is a single dive through the atmosphere, a straight path from space to splashdown. Artemis II used a skip entry instead, the first crewed skip maneuver ever flown. Orion bounced off the upper atmosphere like a stone on water, bleeding speed during the first pass, then diving back in for the final descent. This created two distinct pulses of intense heating that the shield had to survive back to back, not one. The skip maneuver was not optional. It was required to keep gravitational forces on the crew below survivable limits, and to extend the range so Orion could reach the recovery zone in the Pacific. The contradiction is that the skip doubled the thermal complexity. The shield did not just have to survive peak heating once. It had to survive it twice, with a brief cooling period in between. And engineers had no crude data to confirm how the material would respond to that rhythm. During the skip, the shield also had to resist the crushing force of 11 times Earth's gravity, meaning it faced both 5,000-degree heat and structural compression simultaneously. If the material cracked under load, hot plasma could penetrate gaps and burn through to the cabin. The old model assumes the shield remains structurally intact under predicted loads. The unexpected charring from Artemis I raised the question of whether localized hotspots could weaken the structure enough to create new failure modes under higher gravity. The shield creates a bow shock wave in front of the capsule, a zone of compressed air that holds the hottest plasma slightly away from the surface. This invisible force field is why the shield does not have to touch the full temperature of re-entry plasma, which can exceed 10,000 degrees in the shock layer. The material only has to handle the heat that radiates and conducts across that gap. The old model treats the shock layer as stable and predictable. The contradiction is that the skip maneuver changes the shock geometry twice, and any wobble or unexpected angle of attack shifts where the heating concentrates. Artemis I's uneven charring suggested that real-world aerodynamics during skip re-entry might not match the smooth predictions from simulation. For several minutes during peak heating, the crew was out of contact with mission control, encased in a sheath of superheated plasma that blocks all radio signals. This is called plasma blackout, and it is a known effect. The old model is that blackout is temporary and predictable, lasting only as long as the plasma persists. The contradiction for a skip entry is that blackout happens twice, with two separate communication gaps, and if something goes wrong during the first pulse, ground teams have no way to know until the capsule emerges, and by then, the second pulse has already begun. The crew cannot eject, cannot abort, and cannot receive guidance. They are alone inside a fireball, trusting that the shield will do its job without confirmation. As the shield burns, it leaves a trail of glowing red-hot flakes behind the capsule, visible to the crew through the windows. This ablation snowfall is normal. It is proof that the system is working, that material is vaporizing as designed and carrying heat away. The old model is that ablation rate will match predictions within a known margin. The contradiction is that Artemis I's rate did not match in all areas, and the crew of Artemis II had no way to visually confirm whether their shield was ablating evenly or developing the same unexpected patterns. They could see it burning. They could not see if it was burning wrong. NASA officials viewed the shield's performance as the final green light for the entire multi-billion-dollar Artemis program's future. If Artemis II's shield had failed, it would not just have been a tragedy. It would have been proof that the agency could not safely return crews from deep space, undermining confidence in the moon landing planned for Artemis III and every mission after. The old model is that technical risk can be managed through testing and iteration. The contradiction is that crewed deep space missions do not allow iteration. You only get one chance per crew, and the emotional stakes of that finality are what turn the shield into the mission's most charged component. The shield was not just protecting 4 astronauts. It was protecting the credibility of the entire return to the moon effort. When the capsule splashed down on April 10, 2026, intact and on target, the shield had lost only the predicted amount of material. Post-flight analysis measured the exact millimeters of ablation, and this time the data matched the models. That alignment was the technical proof the program needed. The old explanation for why heat shields work is that ablation is a well-understood process. The evidence now shows that ablation at lunar return speeds under skip entry conditions with a honeycomb-packed structure is well understood only when the models are validated by actual flight data, and Artemis I did not provide that validation. Artemis II did. The result still leaves one thing unexplained. Engineers know the shield worked, and they know the ablation rate matched predictions this time, but they still do not have a full, mechanistic account for why Artemis I's charring was uneven. The leading interpretation is that small variations in hand packing density, material cure, or reentry angle created localized hotspots. But that interpretation remains open, because the uncrewed flight did not carry the instrumentation to measure those variables in real time. What the evidence eliminates is the idea that the shield could be trusted on feel or legacy alone. It had to prove itself twice, and the second proof was the one that carried human lives. The shield became the mission's most important story because it was the only system where failure meant certain death, where there was no backup, and where the gap between prediction and reality had already shown itself once. The emotion the crew felt was not relief that the shield worked. It was reverence for the engineers who closed that gap, who took the unexpected charring from Artemis I seriously enough to redesign, retest, and validate the system before putting humans inside. Wiseman's need to hug the responsible engineer was not sentiment. It was recognition that one person's work stood between survival and catastrophe, and that the shield had become the single most emotionally loaded component of the entire mission, because it was the one thing that could not be wrong. For future Artemis missions, every heat shield will now be measured against the Artemis II baseline, and every millimeter of ablation will be compared to this flight's data. The shield is no longer an assumed success. It is a measured one. If you are following Artemis III, watch for how NASA discusses thermal margins and ablation modeling in pre-flight briefings. That is where the lessons from this mission will show up next.